So today we are hosting Daniel Brown, and Daniel will talk about leveraging human input for robust robot learning. And he's a postdoc at the University of California in Berkeley, and he's working with Anca Dragan and Ken Goldberg. And he wrote an outstanding PhD thesis and received the PhD in 2020 from University of Texas in Austin. And he was advised by Scott Niekum. And I also like to give the word to Daniel. So feel free to start. I'll stop sharing my screen.
Okay, thank you. Yeah, super happy to be here. Thanks for the wonderful introduction. Yeah, let me share my screen. Okay, can everybody see me and the screen? Perfect.
Yeah.
Okay, yeah. So just like Sylvia mentioned, yeah, today I'm going to be talking about leveraging human input for robust robot learning. And part of what motivates a lot of my work is this idea that we as people live in a fascinatingly complex and diverse world filled with all sorts of different tasks, different styles and preferences. And we'd like to get our friendly Mr. Robot to come out into the world and help a variety of people under a variety of circumstances, according to a variety of different preferences and needs. And this is really hard. The world is, very complex. And so in particular, I think this motivates some fundamental research challenges that I'm gonna touch on at least briefly today. And so the first one is just how do we represent uncertainty? And in particular, we want, in my opinion, we want robots that know what they know what they don't know, and are able to reason about this uncertainty. We also want robots to be able to be robust to this uncertainty. Ideally, we can have robots that can hedge their bets against multiple possible outcomes and are risk sensitive. And furthermore, we want our robots to be able to not just be at the mercy of lots of uncertainty, but be able to actively reduce that. In particular, I'm going to talk about how they can leverage human interactions to try and learn more robust policies and learn more about the world, more about humans, reward functions, and objectives. So it's kind of a case study for where uncertainty can be useful. This is a project that's been going on for a little over a year now in Ken Goldberg's lab, where we're looking at this idea of trying to grasp novel objects. So if you can think about putting a robot down in a room, there's high likelihood it's gonna, if you ask it to clean up this room, it's gonna find an object it's probably never seen before, and it's gotta learn how to grasp it to put it away. And while there has been lots of really cool work on building these general purpose grasping algorithms, people have shown that there still exist these adversarial objects that, given any training set, you can always find some object that's out of distribution enough that this general purpose grasping algorithm will fail. And so the idea is what can we do here? And so our main idea is exploratory grasping. This idea of kind of being like a child and just picking up objects and playing with them, trying to grasp them in a different way, dropping them to see how they land. And over time, hopefully building up knowledge about how to grasp an object that you may not have a model of, and that your existing grasping algorithm might not be very good at grasping. And so here's an example of how this looks. So we've got a robot, and it's basically just trying out different ways of grasping this object. Every time it succeeds, it picks the object up, rotates its gripper, and then drops it. And you can see it's taking these depth scans, and over time, it's keeping track of different stable poses, different ways the object can rest. And it's learning how it should grasp in each of these stable poses. And so it's trying out these different grasps over time. Sometimes they fail, sometimes they succeed. And over time, it's able to get better and better at grasping this object. And so the way we formulate this is as a standard multi-armed bandit problem, where given a stable pose, a way the object can rest, we can try out different arms, which are essentially different ways of grasping the object. And we get a reward of 1 if we're able to successfully lift the object, and a reward of 0 if the grasp fails. But it's a little more complicated than that, because we actually have multiple multi-armed bandits, because each stable pose has a different set of grasps that may work well or may not work. And so In particular, is this kind of loosely coupled system of bandit problems where every time we grasp it successfully, we drop and we may end up in a new bandit problem where we're now trying different grasps. And so while you can get provable no regret guarantees in the limit as you run like a no regret algorithm per stable pose, the question comes up is like, what if we don't want to run the algorithm for a really long time? How can we have the robot maintain the appropriate amount of uncertainty so it knows when it can stop, when its grasp success is above maybe some desired threshold? And so in particular, we want to come up with these high confidence bounds on performance. And so if I'm dropping this object over and over again and keeping track of the different ways it lands, I may have some kind of probability distribution over what I think the likelihood of these different poses are. But kind of our insight was that, especially early in learning, you also want to keep track of the probability of this kind of like none of the above option, because I likely haven't actually seen all the ways that this object can balance. And so, especially at the beginning of learning, there's a large uncertainty, and we're going to put a large amount of weight on this idea that there are other stable poses we haven't seen yet. And in particular, we're going to do Bayesian inference over what we think the likelihoods of these stable poses are. And so we can sample a certain set of probabilities for how the object might land. And then we know for each of these ways the object lands, we have our current policy, how well it's going to perform. And pessimistically, we're just going to assume that we're always going to have a performance of 0 if we see a pose that we've never experienced before. And so we can sample lots of different likely stable pose drop probabilities given the data that we've seen so far. For each one of these, we can actually say, okay, if this was the true world, how well would my current robot grasping algorithm work? And so over time, we build up this posterior distribution over expected performances across a wide variety of likely hypotheses about what we think the actual drop probabilities for these stable poses are. And then what's cool is then we can then use this to compute a high confidence lower bound on our expected performance. And so in particular, like if I start at the very beginning of exploring this object, I probably have high uncertainty, and there's like a really good likelihood that there are other stable poses I haven't seen yet. But then we speed forward in time. The robot spends a lot of time grasping this object, dropping it, seeing what types of ways this object can land. And then at some point, it's going to be sampling distributions over these stable poses that maybe look like this, where it's very confident, like it's seen everything that it should see. And in all the stable poses that it's seen, it's got like really good performance. It's grasping this object, maybe 95, 96% of the time. And so we can then use this to say, okay, like the robot can stop now. When it's 95% confident, it can grasp the object at a certain threshold, maybe like 90% of the time. So this allows the robot to maintain its uncertainty and kind of know when it can stop. And so this is a cool idea. And I think these are possible, these high confidence bounds in this setting, because in one part of the nice structure of the problem, but also because we know the objective here. We kind of like baked it in, that it's like a +1 when you grasp the object, a 0 when you can't grasp it. And there's this big question of like, what if the robot doesn't know the objective? Can it do something similar? And in particular, there's lots of things that we as people do that it's really hard to write down a reward function for, like driving, making a salad, cleaning my living room, or like figuring out how to lift someone onto like a bed. These are things that it's like really hard to write down a cost function for, but it's often pretty easy for a person to demonstrate these types of behaviors or give feedback on them. And so this motivates the idea of imitation learning, where basically we want to go from human data, whether it be demonstrations or preferences or corrections, and learn a policy that I'll denote by pi. And there's a couple different ways of doing imitation learning. I'm going to kind of loosely break them into 2 different categories, where one on the left is behavioral cloning, where we simply learn to map from states to actions via supervised learning. This is relatively computationally efficient, but can often suffer from compounding errors if the robot sees a state that it hasn't actually seen a demonstrator action in. It may not know what to do. On the other hand, there's this idea of inverse reinforcement learning, where as an intermediary, before getting a policy, we want to learn a reward function that explains what the demonstrator did. And this is nice if we want to try and explain what the demonstrator's rationale is, if we want to think about what the demonstrator's objective function is, and in particular, if we want to like reason about these kind of high confidence bounds and uncertainty. And so especially think about like robustness and safety, I'm going to argue that having a reward function is really handy if we can get that. And in particular, not just having like a single reward function, but kind of one of the main I guess, points of the talk is having uncertainty and maintaining that uncertainty. So we want to have a distribution over likely reward functions that we think the demonstrator is trying to optimize. And this is really important, as we've talked about before, for coming up with these high confidence performance bounds, for performing robust policy optimization, and as well as for active information seeking to try and reduce this uncertainty. And so throughout this talk, we're going to go through and talk about these three different ways that we could use uncertainty. And so first off, let's talk about how we can get performance bounds. Let's see, I'm hearing a little bit of an echo. Is that just me? Let's see. Okay, I think it went away. So weird fluke. Anyways, yeah, we want to have a robot that can bound its performance without knowing the ground truth reward function. And that's kind of the main difficulty here. If we had a cost function, then things become a lot easier. And so we want to represent our uncertainty over what we think this reward function, or alternatively cost function is. And so we're going to take a standard kind of Bayesian inverse reinforcement learning approach, where we want to learn this posterior distribution over likely reward functions given our human data. Let's just say demonstrations for now. And so we have a reward function R, we have the data coming from the human D, and we know via Bayes' rule that this is proportional to this likelihood function, the likelihood of seeing this data, given that the human's trying to optimize the reward function R. And then we can have some prior knowledge if we wish in terms of prior over what reward functions we think a priori are more likely than others. And the goal here is to sample likely reward functions given this human data. And so in particular, if we want to bound the performance loss of the policy, ideally we want to say something like this, where we have some small delta. We say, hey, with probability 1 minus delta, the difference in expected value, so denoted by V, of running an optimal policy, pi star under the demonstrator's true reward function. And if we take the difference between that and running the robot's policy and evaluating it under the true reward function, we want that to be small. We want the robot to not lose very much performance when it's running its own policy as compared to the optimal policy when evaluated under R. And the problem here is that we don't know pi star. We don't know the human's optimal policy. We just get some samples. And we also don't know the human's true reward function. That's assumed to be kind of inside their head, and we can't introspect that. And so one natural idea is let's run Bayesian inverse reinforcement learning to get a distribution over reward functions. Then the question becomes, which one should I pick? We still don't know which reward function is the right one. And so kind of an idea that we had early on in my PhD was that we can sample a lot of likely reward functions. And then for each of these, we can kind of run this counterfactual, and we can say, well, maybe this reward function was the human's true reward function. If so, what would their policy look like? And then given any robot policy as input, we can then calculate a hypothetical policy loss that says, okay, here's my policy. Here's what I think the human's policy might be. How much return, how much reward do I lose by running my robot's policy versus the optimal policy under this hypothesized reward function? And in particular, we can do this for multiple reward function samples and compute these hypothetical policy losses, which then gives us this distribution over policy losses across this range of scenarios. And then we can take this notion from finance, which is called value at risk, which is essentially, you can think of it as just like a high confidence bound. And so we can say, with high confidence, my performance, on average is no more than, no less than a certain amount, or my policy loss in this case, we want to bound, upper bound that. And so we can take all these sample policy losses, we can sort them, and then just create a 95 percentile cutoff and say, okay, 95% of the time, my policy loss is less than X amount. And people have tried to do similar approaches using different techniques. And what's cool is we found that using this Bayesian inference approach ended up being orders of magnitude more efficient in terms of the number of demonstrations that we needed to get these nice tight confidence bounds. But the natural question here is, is this tractable in practice? And there are some problems here, because if you look at this likelihood function a little more closely, this is the likelihood of the demonstrator producing demonstrations D when trying to optimize R. And if you know anything about reinforcement learning, this probably sounds really familiar. This is kind of the reinforcement learning problem. This requires solving for a policy given a reward function. And this is known to be really hard. Yet we have this baked into kind of our inner loop of Bayesian IRL, where every sample we want to generate from this posterior is going to require us to at least partially solve an RL problem. So we were interested in trying to see if we could do this more tractably. And one of the ideas that we had is, what if we had a different type of input? Rather than just demonstrations, what if we had ranked preferences over a set of demonstrations? And this is nice for a couple different reasons. One is that it allows extrapolation and works with suboptimal demonstrations. So typical inverse reinforcement learning algorithms are going to take the human data and they're going to say, okay, let me try and come up with a reward function that makes what the demonstrator did look optimal or near optimal. But if the demonstrator is struggling with the task, then that might lead the robot to infer an incorrect reward function that tries to rationalize the mistakes the demonstrator made. But if the demonstrator is able to give like a variety of demonstrations and then rank them and give preferences over them, then there's this possibility that we can actually explain this ranking by learning a reward function that allows us to extrapolate, and we're not tied down to doing exactly what the demonstrations did. And also, as I'll show, this makes it a lot more efficient having these ranked demonstrations, and it's not going to require us to have a reinforcement learning algorithm or like a planning problem in the inner loop. And so we call our method trajectory ranked reward extrapolation, or TREX, where the idea, as I mentioned, is we have a set of pre-ranked demonstrations. So in this half theta domain, we want this little simulated robot to run to the right as fast as it can. And we give it a set of ranked demonstrations ranging from pretty awful, just kind of scooting along the floor on its head, to like mediocre, where it's kind of running, but every once in a while, kind of like a toddler, you know, trips and falls. And so we give it a set of like maybe 10 or 15 of these ranked demonstrations. And then we learn a reward function. And then when we optimize that reward function, we get a policy that ends up being much better than the best demonstration. In this case, running about twice as fast and far as the best demonstration that we've seen. So let's kind of dig a little more detail about how this works. So we're going to assume that we have a set of ranked trajectories, which I'll denote by tau. And if we take any two, I have this preference over tau2 versus tau1. And so what does that mean? So one way of interpreting this is saying that if I look at the states in trajectory 2 versus trajectory 1, my rewards that I assign to these states should be higher. So I want to assign a higher reward to better ranked trajectories. And we can nicely optimize this using just a standard pairwise ranking loss, where we're trying to make the exponential of the accumulated reward for the better trajectories much higher than the accumulated rewards for the worst trajectories. And one way of thinking about this is you can take the returns of these trajectories and think of them as logits in like a cross-entropy loss. So we're kind of solving this classification problem that says, given two trajectories, which one do I prefer? And the idea being, if I can solve that classification problem by assigning rewards to individual states, I basically have to kind of pick up on like what are good things and what are bad things in these trajectories. And here's an example from Atari, quote unquote autonomous driving in Atari, where basically we're learning from pixels given a set of 12 demonstrations, where this is the best one I'm showing on the left. So, you know, it's not bad, but it's, you know, kind of hesitant at times. And as you'll see later, like occasionally gets a little out of control, crashes into cars. Whereas the policy that we're able to learn using TREX, once again, you know, using no score information, we're masking that, is able to perform much, much better. And it's able to pick up on the intent of the demonstrator from these suboptimal ranked demonstrations. So this is all like really well and good, but what we also noticed is that occasionally you can get these really weird behaviors that we kind of call these reward hacking behaviors, where the agent does something that it thinks is good, but is really not probably what the human intended. So in the Pac-Man game, you're trying to run around, right, and avoid getting eaten by ghosts and eat many pellets. But when we tried giving ranked demonstrations to our algorithm and then training it, what we found is that it found this really cool loophole, is that you can like tunnel and go back and forth between the different sides of the screen. And that ends up kind of confusing the ghosts, and you can live for a really long time and not get, you know, eaten by the ghosts, but you also don't really, you know, do what the game is intended to have you do. Similarly, for this like Beam Rider game where you're flying a spaceship trying to shoot down enemy spaceships, the RL algorithm learned that if it kind of mashes its keys and goes left and right really fast, it actually stays out of the firing lanes of these enemy spaceships and is able to live for a really long time. And so while maybe living for a long time or avoiding getting shot or eaten by a ghost is correlated with the demonstrator's true intent, it's probably not causal. And so one of the problems here is that TREX is just finding this maximum likelihood estimate of the reward function, and it might attach this reward function to the wrong features, because there's no consideration of alternative hypotheses. There's really no uncertainty here. And that's kind of what we want if we want to try and avoid things like this. So the question here is like, can we combine the best of both worlds? For T-Rex, we have this computationally efficient algorithm that can give us better than demonstrated performance, but it doesn't have uncertainty. Whereas earlier I talked about this kind of classical Bayesian IRL approach, which is often computationally inefficient because you're running reinforcement learning repeatedly. And it often is just trying to find a reward function that makes the demonstrations look optimal. But it does give you this nice posterior distribution, which enables you to think about risk and uncertainty. And so can we get the best of both worlds? And to try and do this, we proposed an approach that we call Bayesian REX, or Bayesian reward extrapolation, where essentially the idea here is we're going to take the same kind of input that we had for T-Rex, so a set of ranked demonstrations. In this case, this is like an Atari domain, so we have these visual inputs. And we're going to train this kind of convolutional network backbone to try and pre-train some features, kind of embed these high dimensional inputs into a lower dimensional space that will allow us to do tractable Bayesian inference. And the way that we do this is via a set of self-supervised task losses. And so we train like an autoencoder. We have like a temporal distance loss function that's trying to predict, given one trajectory, how far apart are two states from that trajectory, as well as an inverse dynamics and forward dynamics. And each of these has a separate head, but we're using the same feature embedding to try and train these different losses. And we also train it on the standard supervised learning, this pairwise ranking loss that I talked about earlier, given these ranked demonstrations. And so the idea being is if I can try and minimize all these different losses by using the same feature embedding, hopefully this is going to be a rich embedding space that allows me then to like think about multiple hypotheses that explain these demonstrations. So in particular, yeah, we freeze the initial part of this neural network, and now we just have a linear reward function. So we're just learning this last weight, this last vector of weights, this last layer. And so we have this linear reward function given our embedding, and then some weights on top of that. And so what's nice about this linearity is we can embed these demonstrations and just kind of run them through this network and accumulate these kind of latent embeddings. And we can do this as like a pre-processing step. And so now every time I have a reward function hypothesis that I want to evaluate, this is essentially just a weight vector in a much lower dimensional space. And the crux of like doing this sampling, this Bayesian inference, is thinking how likely is this sample's reward function? And this essentially amounts to just plugging in that weight vector into this pairwise ranking loss. And so what's nice about this is essentially I can I can take a weight vector and I can say how well does it match my supervised ranking labels. And this doesn't require me to actually run anything in the MDP. I'm just kind of like taking scores that I hypothesize and seeing how well they match up with the actual ground truth preference labels. So this enables us to do really fast Bayesian inference to sample from a wide variety of reward functions that make sense given the demonstrations. In particular, we're able to sample 100,000 samples in around 5 minutes. Whereas if you were to do a classical Bayesian IRL approach that has RL in the inner loop, it could cost you 5+ hours just to generate one sample. And so this is like really cool. That makes things a lot more scalable. And in particular, we can use this to do things like, we can rank different sets of policies by using high confidence performance bounds. So one thing we did is I gave like a set of trajectories ranging from good, so me trying to play the game beam rider well, a mediocre demonstration that does okay, but occasionally gets hit by the enemy's bullets. I produced a deceptive demonstration where I tried really hard to like move around and shoot, but not hit any of the aliens to see if that could like trick the network into thinking this was good. And then a pessimal example that just gets hit by the enemy spaceships right away. And so using this distribution over potential reward functions, we can now rank these in terms of high confidence bounds. And we do get a good ranking in terms of the good one being the best, and then the pessimal being the worst. And in particular, the network is not deceived by this deceptive one that looks like it's playing the game but isn't. And we've also shown that you can also use this kind of method to detect this kind of reward hacking behavior. Well, you'll notice that the distribution over actual returns that this policy gives is like very large. It has very high variant. And so these high confidence bounds are like very loose. And that's like a good indicator that something might be going on that's a little fishy, and your policy might be only doing well under a small number of reward hypotheses, but kind of ignoring other ones like maybe getting rewarded for shooting the enemies in this game. And so here we've talked about kind of these high confidence bounds and how we can maintain uncertainty, but there's still a lingering question about, what should the robot do if it's not confident that it has good performance? And like in particular, can the robot actually like optimize its policy in a way to make it more robust? So I'm going to kind of transition now to this idea of robust policy optimization, where we want to take a distribution and we want to optimize the policy to be robust under this distribution, rather than just being robust under like a certain sample. And there's two ways of doing this. We can be robust, or we can also actively query to try and reduce our uncertainty, where we have the robot ask for help. And so first we're going to talk about this idea of being robust to uncertainty. And so the motivation here is that human input is often highly ambiguous. If I see just a couple demonstrations or get a couple preference labels, there's probably a lot of room for error, a lot of ways of interpreting that. And so the question here is, how should the agent act if it has uncertainty over what its objective is, over what the true reward function is? And so we proposed this approach back in 2020 called Bayesian Robust Optimization for Imitation Learning, or BROIL, where essentially we're going to have an objective that tries to balance between risk sensitivity and expected performance. So if you think about a car driving down the road, if it notices this box along the freeway, there's a lot of uncertainty over how much damage it might do if I try to run over this box. Maybe it's just like an empty box and I'll just crunch it and keep on going. Maybe it's filled with something, and so there's a lot of kind of uncertainty here, and there's a potential that I could actually damage my car. And so a robust policy will kind of think about these different costs that it might incur, and we'll probably learn to avoid the box. If you have like a different example, like maybe just a household cleaning robot, and it sees this object on the floor it's never seen before, sure, there might be like some small probability that this is like a leopard that might eat the robot, or like maybe lava, but probably not. And so in other circumstances, you may not want to be quite as risk sensitive, and you may think, okay, it's okay to drive over this kind of weirdly shaped tile on the floor. And so how do we measure kind of risk in these cases? So we've talked a little bit about kind of at a high level this idea of value at risk, where it's essentially finding like a worst case quantile. So given some alpha, if alpha is 0.95, then essentially the value at risk is like a 95 percentile bound on my performance. And it turns out this is kind of nice and intuitive, but optimizing for it can be difficult. And so what we use instead is this idea of conditional value at risk. And so conditional value at risk says, condition that I'm in the tail. So I'm in say maybe the worst 5% of my distribution over performance. What do I expect to happen? What's my expected performance? And the nice thing about this is this results in a convex optimization problem, which makes it really nice for policy optimization. And so in particular, we're going to try and blend between this idea of balancing our expected performance, because we want to do pretty well on average often, but we also have this conditional value at risk. You can think about this as like the tail risk, like what might happen kind of in the worst case scenarios. And we're going to blend between this via this lambda parameter, where if lambda is 1, we're just going to focus on expected performance. Whereas lambda is 0, we're just going to focus on just minimizing tail risk. And in between, we're going to kind of try and balance both. And so what's cool about this is you can actually efficiently solve this objective via linear programming for discrete MDPs. But often in robotics tests, we want continuous actions, continuous state spaces. So we've also shown recently that you can extend this idea to a policy gradient style approach, where if you're familiar with reinforcement learning, you can kind of look at the math. If not, I'll try and keep things at a high level. But basically, policy gradient approaches are going to look at the advantage, like how much better you think taking an action in the state is opposed to other actions. And they're going to try and increase the likelihood of the policy in taking actions that are good, that have high advantage. And this is like a vanilla policy gradient approach. What we propose is something very similar in form, except we now have this tail risk weighted advantage. So I'm going to weight more heavily reward functions that I think I'm performing worse under. And in particular, every time I roll out the policy, I'm going to look and say, okay, which reward functions am I now performing the worst under? And I'm going to try and optimize my performance under these reward functions. And this is nice because you can just kind of bake this into most standard policy gradient style algorithms. And so if we think about a nice motivating example here that's easy to kind of visualize, we have this navigation example where I have a known goal here as the star I'm starting here. And this gray region is a region of uncertain cost. An expectation, I think it's not going to be that costly, but kind of in the worst case, this could be really costly for me to drive over. And so as I vary lambda, I can range from something that minimizes my expected cost by just kind of driving straight, kind of finding a shortest path. And then as I decrease lambda, I'm becoming more and more risk sensitive, where I'm trying to avoid the gray region, but I don't think it's worth it to go all the way around. And then finally, when I have lambda equals 0, I'm actually optimizing a policy that is very careful about avoiding these regions that might have a really high penalty. And this is a continuous kind of two-dimensional problem. We've also shown this scaling to things like Atari games, where here we're training from suboptimal demonstrations using Bayesian Rex to get our posterior. And then we're optimizing a policy with respect to that entire posterior to get a robust policy that performs better than a lot of other methods that we found. And so kind of to wrap up, I want to briefly talk about this idea now of, can we actively query the human to reduce uncertainty? And so one thing that we can do is we can kind of close the loop here. So we're going to be actively sampling now. We're going to be asking for more and more data. And in particular, we want to ask for data in states that have high risk or high uncertainty. And so one example that we had was trying to learn to place a vase on the table, where here there's a lot of uncertainty over what matters. The robot might think that it should be between the blue cup and the red bowl, or maybe it should be in the center of the table. In this case, like the true reward function is to set in the center of the table, but the robot doesn't know that. And so it asks these risk-aware active queries. And over time, it's able to actually learn what the true desired reward function is, which is just place it, not hitting the other objects, but on the center of the table. And what's cool is we can actually maintain an upper bound on our actual performance loss, our placement error. And this is actually ends up being a pretty tight upper bound, which is kind of cool. And so the idea being here is, if I have like a safety threshold, going back to the early kind of discussion on this exploratory grasping result, something similar where I can have a robot that knows when it should stop because it has some desired threshold of error, and once its policy's upper bound it gets below that, we can actually stop. And so this is kind of cool. It's one of the first examples of robots kind of knowing when they have enough demonstrations. We've also looked at this idea of how robots can assist people while performing this active learning over reward functions. This is motivated by this idea of assistive autonomy or assistive robotics, where this is an example video I found of this young woman who was born with muscular dystrophy. And so she uses this wheelchair and has this robot arm, and she's able to perform a lot of really complex, really interesting tasks. But you can see it's a really complex control problem for her in order to perform tasks as simple as getting a drink of water. And so this really kind of motivates this idea of assistance via shared autonomy, where we have a user providing inputs, but we also have a robot that's making predictions about what they think the human's true intent is, what they're trying to do. And we can blend these in order to decide what the robot's action should be. And so in this case, the robot can help the human if it thinks it knows what the human's trying to do. But there's an issue here is, what if the human does something unexpected? So in this example, the robot knows about these two different goal locations shown in purple and green. The human's now deciding to do something different. They want to pour this cup over in this unknown skill region. And you'll see if you watch this video that basically as the human starts to teleoperate towards this red goal, the robot becomes very confident that it's trying to go to the green goal, and it just kind of takes over and says, hey, let me help you out. I'm going to pull you in, and really hinders the human rather than helping them. And so kind of the crux of the problem is that the robot's not appropriately taking into account uncertainty here. And in particular, it's not considering this kind of none of the above option, that maybe everything it knows about is unlikely. And so what we propose to do in these cases is, if the robot detects an unknown intent, something that doesn't really make sense given the set of reward functions it's learned, that it should let the user operate, kind of give control back to the human, and then actively learn from the human demonstrations. You ask, hey, can you show me that task a couple more times? And then it can add this new reward function to its skill library. So the next time the human tries to do this novel task, it's not novel anymore. The robot kind of knows what the human's trying to do, and it can say, hey, let me help you out. And so we ran a user study in simulation where we did find this happening. So before learning, we have our algorithm, and you'll see here, this is the number of keys is showing kind of the human effort as they're teleoperating the system. And at some point the robot just kind of stops and says, okay, I'm just going to like let you control the system. I'm going to learn from you. And so you can see it takes a large amount of keystrokes for the human to accomplish this, but the robot actually like doesn't hinder them. Whereas after learning, we now know about this like new skill the human might do. And so you see the human starts moving in that direction. And at some point, the robot says, okay, I kind of know what you're trying to do. And the robot takes over, and the human can kind of just like sit back and and the robot can accomplish this task for them with much minimal effort. And yeah, so I think I'm kind of running a little short on time. So I'm going to quickly just kind of like skim over a couple of results here, which are some other ideas that we've had where basically, running RL is not always the best thing that we want to do. Sometimes it's unsafe if I have to explore a lot. And if every time I get new human data, I have to run RL again, this can be really expensive. So we've actually done some work recently on interactive imitation learning, where I'm running behavioral cloning, but I'm still maintaining uncertainty over what actions I might want to take. And in particular, I'm going to ask for help in actions that I think are risky or unsafe. And so as an example of this, basically our algorithm is going to take in a state, and we're going to learn a predictor that says, is this state novel? Is this state like dissimilar from things that I've seen before in the demonstrations? Or is it risky? And if it's either novel or risky, I'm going to ask the human to help me out and kind of teleoperate. But if it's not, then I'm going to assume, hey, my policy is okay, and I'm going to run my own robot policy. And in this way, I'm going to actively query for help in states where I don't really know what to do, or where I think I might like fail. For example, in this like peg in the hole task, like the robot, notice this is risky because it's kind of lost the little washer that's trying to put over this peg. And so in particular, we have the robot, it's in autonomous mode most of the time, but sometimes when it fails, for example, it might get into a novel state. It's going to ask the human supervisor to take over. And then once it kind of gets back into a state where it knows what to do, it goes back into autonomous mode. The human can go off and do a different task, and then the robot can accomplish the task here. Sometimes, maybe even like the initial starting condition is new to the robot. So it might say, hey, can you help me out? I think this is kind of a risky maneuver for me. And then at some point, the robot goes back to autonomous mode. It takes over, and it's able to accomplish the task. And so, yeah, so in summary, so we've talked about efficiently representing uncertainty, this idea of robust policy optimization, as well as the idea of actively reducing uncertainty. And yeah, I'd really like to thank all my lab members and my advisors, Anca, Dragan, Ken Goldberg, and Scott Niekum, who have been great mentors through this process. And I'm going to end now and open up for questions. Thank you.
Thank you, Daniel. It was a really great talk. You covered a lot of topics, really. Do you have any question? We have a question also in chat. Tina, do you want to ask the question?
Yes, sure. Thank you very much for this very interesting talk. I was specifically interested in the shared autonomy scenario that you showed, where the robot manipulator was providing assistance to a human. So my question is, how did the robot detect that it should let human take over control?
Yeah, that's a great question. So the robot here, we're assuming that it's learned a set of kind of a library of reward functions that correspond to different tasks the human might be accomplishing. And basically the robot is looking at the human's actions, and it's evaluating their likelihood under these different reward functions that it knows about. And essentially what it's doing is thinking about, okay, like how optimal does a human look given these different reward functions? And if it can detect that like the human's taking actions that don't really make sense given any of these reward functions, then it has like really low confidence that any of these reward functions is like the human's true intent, and it will just kind of like give over control to the human. And so the way it balances its kind of share of the control is based on its confidence that it knows what the human's objective is. Does that answer your question, or?
Yeah, it does. Thank you. So in the lab where I work, we also used brain signals for detecting surprise. and use that also as a feedback to the robot. Yeah, thank you.
Yeah, very cool. Yeah, I think, yeah, using like lots of different modalities is something that, yeah, I'm very interested in the future. We kind of talked mainly about like demonstrations and preferences here, but yeah, I think there's a wide variety of like human input signals, like, yeah, brain scans, I think natural language, things like corrections that I think, yeah, ideally we can use all of these in order to get like a really good model of what maybe a human's trying to do so we can assist them and learn from them.
Yeah, I think that would be amazing.
Yeah.
Thank you.
Thank you once again. We have another question from Guy. Guy, would you like to ask?
Hi. Yeah. Thanks for this really interesting talk. There was a lot there. I was sort of curious about the first part with the Bayesian inverse reinforcement learning, and what kind of assumptions you have to make on the reward function or the structure of the reward function. And so it was kind of really hard to follow through all the projects. In some cases, you had just a vector of weights on different rewards, but in others, it seems like it has to be somewhat neatly parameterizable. Or am I wrong about this? Like, what does the reward function look like for this to work?
Yeah, that's a great question. So I would say, yeah, to get like kind of classical Bayesian IRL to work, it's maybe like not as much about like the reward function as it is about the difficulty of solving like the forward problem of saying, given a reward function, what is my policy? So Bayesian IRL kind of in general doesn't assume like a linear combination of features, but having a linear reward function does make things like policy evaluation a lot easier, because if you think about like the value function given a reward, if the reward is a linear combination of weights, then my value at a certain state is simply like this weight vector multiplied by like the expected features that I might see running my policy at that state. And so we can calculate things a lot more efficiently via dot products. And so, yeah, so one of the ideas with Bayesian Rex was we wanted to keep this efficiency of having like a linear reward function, but we wanted it to be very expressive. And often people just kind of handcraft very simple features for learning. And so instead of that, we have this idea that you can kind of see here in really small text, where basically we're like pre-training a network. So we're assuming that we have a linear combination of features for a reward function, but these features are highly nonlinear, very complex features built up of multiple convolution layers. And we found this to kind of be like a nice kind of balance between just having like a very complicated reward function that might be like kind of end-to-end trained versus having like a very like simple set of handcrafted features. And so, yeah, the nice thing about having a linear reward function here is we're able to perform these high confidence bounds really efficiently, but we can also deal with high dimensional inputs like images. And so I don't know if that, answers your question. If not, we can dig into that more.
Kind of just like a short follow-up. Do you, I mean, if you have to represent the probability of anything over the reward function as your variable, doesn't the reward function has to be somewhat structured as a variable, so it can, or do you never explicitly have to like discover the probability of the data given the reward function, etc.? That I might be missing.
So definitely like we want to have a distribution over reward functions, and so having things be like linear and low dimensional is helpful, just because I probably don't want to store 1,000 million parameter neural networks that each represent like a different reward hypothesis. It's much more efficient if I can just like keep some uncertainty over like the last layer in a neural network, or like if I had handcrafted features, keep the uncertainty over that last layer. And so while in theory, you could like have like arbitrarily complex reward function models that you keep uncertainty over, this often becomes intractable in practice. And so I think that's why often people are drawn towards these like simpler kind of linear reward functions. I think the limits there are that often people kind of have to craft these features themselves, and so they might be missing things. And so kind of our idea here was like, maybe we can like try and learn these kind of low dimensional reward functions that make this Bayesian inference more tractable, because we're keeping track of uncertainty over a smaller number of parameters, but still hopefully like more general in terms of having more expressivity as a reward function.
Thanks.
Thank you. Do we have other questions? If not, I have a question actually. So I was wondering if we can use some, like extend the demonstration in some way by using other form of abstraction for describing the agent behavior, like, for example, even like taking evaluative feedback or explanations about the behavior of the agent to select what are those and to rank the demonstration in some way. So to enrich the demonstration itself by giving some extra things that can serve as a ranking parameters.
Yeah, I'm not sure if I understand fully. So it sounds like you're asking
If
something
we
about like
can,
explanations and about whether you can use those to rank
yeah,
like robot behavior.
yes, like because I think like explanation can be like if the agent can, for example, give an explanation about his own behavior, could kind of select what are those more important aspects of the demonstration that you are trying to extrapolate, and in this way reduce the sample size, because I would give you a higher level or a higher description of my behavior in order for you to generalize and get a bit more of information than what I could give you by just giving you the demonstration. So I'm wondering if you can, if you ever thought about this, and how would you think about this integration? Because it's a bit more what I'm looking for.
Yeah, so I think, yeah, like kind of two things, yeah, that come to mind. Like I think, yeah, if the human is able to like give an explanation to the robot in terms of like some kind of like high level task description, then yeah, I think that can be like really powerful. I mean, yeah, one way you could use that, right? Like even if the human's like maybe not an expert at the task, they could say like, here's what I'm trying to do.
Or why I did that.
Or here's why I did that. Yeah, and so I think that like definitely like is a really strong signal. I think figuring out how to like convey that explanation to the robot could be difficult. Like the easiest thing would be natural language for the human to give an explanation, but I think that's like a really interesting area of like how do you like ground that natural language.
Yeah.
But I think, yeah, that definitely like is like a really kind of powerful way that we teach other people is like, yeah, we kind of explain, yeah, here's why I did this, here's what I was trying to do. I think also having robots kind of on the flip side of the coin, like having robots that can explain what they're doing, I think is really powerful. And I think, yeah, really key for like having like robustness and safety and autonomy is having these systems that ideally like can kind of explain what they're doing, maybe in natural language, maybe in other ways that are like interpretable to humans. And so I think having this kind of like two-way kind of explanation, I think would be really powerful. And definitely, I think, yeah, could help significantly like speed up learning in a lot of settings. But I think, yeah, it sounds like a really hard but really cool, yeah, research problem.
Yeah, but I guess it's a bit like too difficult to integrate with this approach of ranking the demonstration, I would say. Like I was thinking like, could you use this for ranking your demonstration in some way? But that's
so I think you could. I think, yeah, the main difficulty here seems to be yeah, like grounding your explanation into like a reward function over trajectories. So like if you can ground like the explanation that like, you know, I did this because I was trying to avoid knocking over a coffee mug or something like that, or I did this because I was trying to like grab this object, then if you're able to like ground these explanations into like something about reward functions or about like preferences over trajectories, then I think you can then, yeah, use those preferences to learn a reward function better. And so I think, yeah, it seems like, yeah, the main piece there is like, how do you go from explanations? And I think, yeah, if you can turn the explanations into a reward function, then that like allows you to like, or into like a preference over, yeah, trajectories, that would be cool.
Yeah, there is something about that, but not, I mean, I don't know. Yeah, I was wondering in inverse reinforcement learning approaches, not so much like, which is, I think, the most powerful way because it's better for integrating and for learning from humans, I would say. Okay, I think we are running a bit out of time. I will now introduce share again my screen, and thanks again all of you for joining today, and Daniel once again. If you have any other question, we will take them on Slack. We have a specific channel for Daniel, so maybe we can share again the link, and I will now share. So our next session will be with Mika Coran from NASA, and will be on the 15th of October. So we will all wish to have you there. And thanks once again for joining today, and thanks Daniel for the great presentation.